everyone, and thanks for watching Edupedia World Videos. This is the second lecture in the topic Fluid Dynamics, and in this lecture we'll study the most important topic, buoyancy, which was first discovered by Archimedes. So if you have some liquid and you have a light object in that liquid, by light I mean that the density of the object is smaller than the density of the liquid, then it has a tendency to float at the surface. And if you want to put it at the bottom, you need to give it a downward force. You need to push it downwards so that it stays downward, otherwise it comes up. So this was explained by the principle of buoyancy. And I could just give you the formula, but the argument is slightly subtle as to why the buoyant force is what it is. And I think it's important to know that. So let's look at that for a second. Let's say there's some liquid. And let's say I haven't put anything in it yet, there's just some liquid. If I take this particular region of liquid, that region is in equilibrium. That means the net force acting on this by this other part of the liquid has to net be equal to mg, where m is the mass of the liquid, mass of this particular region of the liquid. Now it might be some coming from the right, from the left, upward, downwards. The exact forces by the liquid don't matter, and they're actually quite complicated. All we need to know is that this block has a downward force mg acting on it, and it has other forces acting by the other parts of the liquid, and it is in equilibrium. So the rest of the liquid must be applying an upward force mlg on this liquid, right? Now just imagine we've replaced this liquid by a cube of ice, which has a mass, let's say mi, for the mass of ice. We know ice is less dense than water, so ice cubes float on water. Now the argument is that the rest of the liquid does not know whether this portion of the liquid is occupied by the same liquid or it is occupied by ice now. So this particular rest of the liquid will still apply the same force on this part regardless of whether this is water or ice, because this liquid doesn't care. So if there was no ice, instead it was pure liquid, this particular small part of the liquid would have experienced a force mlg upwards. So this total ice will also experience the same force mlg upwards, not mig, mlg. Because for the rest of the liquid, it doesn't matter whether this particular part is covered by the same liquid or by ice. The rest of the liquid will still apply the same force. All the surfaces are the same, these pressures are the same, everything is the same. So what that means is, if we have some liquid and we have an object in that liquid, whether fully submerged or partially submerged, the net buoyant force, this force is called the buoyant force, the net buoyant force will simply be equal to the force applied on this particular section of water if this was pure water or pure liquid, as opposed to, let's say, a rubber ball. And in that case, the buoyant force would have been mg upwards, which would have been equal to the mass of the liquid upwards multiplied by g upwards, or weight of the liquid upwards. So in any case, whether or not this is water or a rubber ball, the buoyant force is equal to the weight of the liquid displaced. And now in this region we could have a particular sphere made of water, in which case it has to be an equilibrium. So obviously the buoyant force will be weight of the liquid displaced. This could be an iron ball, this could be a cotton ball, this could be a wooden ball. It doesn't matter, the buoyant force will always be the same, the weight of this particular volume of liquid. Okay, so the buoyant force does not depend on the mass of the object we've put in it, but it does depend on the volume of the object, because the greater the volume, the greater the weight of the liquid displaced, the greater the buoyant force. And this is sort of how you can see the principle behind ships floating on water. They do have a large mass, but comparatively they have an even greater volume because of a lot of hollow space in them, and so the overall density of the ship, even though the density of the material iron is much greater than the water, the overall density of the ship becomes less than water. Because if you have a ship like this, and let's say something at the top, doesn't matter. If you have a ship like this particular material, iron, is much denser than water, but this total area is hollow. So the net volume is so much that the mass by volume density of this particular ship becomes less than the density of water. So I hope now you've understood the concept behind why the buoyant force is equal to weight of the liquid displaced, because the rest of the liquid doesn't care whether this volume is occupied by water or any other material. It will apply enough force so that if there was water in this place, that water would have been in equilibrium. And the force required to do that will be the force which it will apply regardless of what the material is. Let's look at this now a little bit more quantitatively. So let's say we have a liquid, the density of the liquid is rho L, and we have a solid in it, the density is rho S. So there will be a downward force acting on it which will be equal to mg. Mg can be written as rho S times V times G, where V is the volume of this ball. That will be the downward force. The upward force will be the buoyant force. The buoyant force will be equal to the weight of the liquid displaced. That is G multiplied by volume of the liquid displaced. Okay, I'm sorry, mass of the liquid displaced. Mass of the liquid displaced will be volume of the liquid displaced multiplied by density of the liquid. This is the biggest difference. This is gravity, which depends upon the density of solid. This is buoyancy, which depends upon the density of the liquid. So net force acting upwards will be rho L minus rho S Vg. This is the net force acting on this object upwards. If rho L is greater than rho S, that means the object will experience a net upwards floats. That means its tendency will be to float. If rho L is smaller than rho S, for example, if the liquid is water and the object is iron, then rho S will be greater than rho L. This whole term will be negative. That means the net force will be downwards, and that means the object will sink. So rho S greater than rho L means sink, and rho L greater than rho S means float. This is the basic principle on which all buoyancy follows. If the density of the liquid is more than the density of the solid, then the solid will float, otherwise the solid will sink. If it sinks, what will happen? It will just keep on going down until it eventually reaches this particular bottom of the container. Then there will be no buoyant force acting on it, because there is no liquid below it to act any force. But then that particular force will be balanced by the normal force applied by the container, just like when an object is kept on a table. What happens when it floats? That's slightly more interesting. If it's floating, that means this should go upwards, but it will obviously not go upwards forever. It will just stay in the liquid. So what happens is, once it reaches the surface, it still has a tendency to go upwards. So now mg will remain the same, but as it is going upwards, the volume inside the liquid is decreasing, because there is some volume outside the liquid. If this is a liquid and I have a solid kept on it, this is the only volume displaced by the liquid. The upper volume doesn't matter. So the buoyant force will now be equal to rho of the liquid multiplied by this smaller volume multiplied by G, not the total volume, right? So if rho S is greater than, if rho L is greater than rho S, it will go upwards. After a point, the volume submerged will start decreasing. So even though rho L is smaller than rho S, the volume submerged, which earlier was equal to the total volume because it was fully submerged, now will be lower than V, and there will come a point when rho L into Vs, volume submerged, will be equal to this, and it will float. So if you take an extremely light object and put it in a liquid, it will probably be something like this, where this is a very small volume and the buoyancy will only be applying on this volume, so that the total buoyant force will be rho of the liquid multiplied by this volume V small, but the gravity will be rho of the solid multiplied by total V, and they will be equal. So whenever you put an object in a liquid with the object's density being less than the liquid, it only floats partially submerged, such that the weight of the liquid displaced by the submerged part equals the gravitational force. However, if an object has density greater than that of water, it will always sink and it will always reach the floor. So let's just look at a very small example. if we take some water and we put an ice cube in it, let's say the total height of the ice cube or length is L, and we want to find out how much part is covered in water. You can do this at home, it's a very easy experiment to do. So all we want is the buoyant force to be equal. So rho liquid multiplied by x multiplied by L square, since this is a cube of side L, this is the volume, multiplied by G, is equal to rho of ice multiplied by L cube multiplied by G. And what we get is x is equal to rho I by rho L. We know that rho L is 1000 kilogram per meter cube, density of ice is 900 kilogram per meter cube, so it is 9 by 10 L. So whenever you put a piece of ice inside water, 9/10 of the part will be submerged and 1/10 of the part will be upwards. This, I don't know if you've heard this before, but there's a very famous saying that you can only see 1/10 of an iceberg whenever you see it. Whenever you see an iceberg on the sea, it'll be something like this. You can only see 1/10 of it. 9/10 of it will be submerged. So whatever size of the iceberg you see, the actual size will be 10 times that. Because the upper part will only be 1/10 of the total length, 9/10 of it will be lower, because the density of ice is 9/10 the density of water. If you could find a solid whose density was half the density of water, then it will always float in water, with half of it being submerged and half of it being above water. Right? So this is sort of the basis of the Archimedes principle as well, which says that when a body is partially or fully dipped in a liquid, the fluid exerts an upward buoyant force equal to the weight of the liquid displaced. Right? What is the weight of the liquid displaced? It will simply be the mass of the liquid displaced multiplied by gravity. Right. Let's move on to the next topic. Now we will break our tradition a little bit. We were just talking about liquids at rest. Now we will talk about liquids in motion. Right? Liquids which are accelerating, in other words. So let's say you have a liquid. You have these 2 points, P1, P2. The distance between them is h. If this whole liquid is at rest, we know that P2 is equal to P1 plus rho GH. Right? Or P2 minus P1 is equal to rho GH. What if this liquid or this whole container were now kept in an elevator, and that elevator was going up with an acceleration A? What would be the answer in that case? First of all, I can simply use my concepts of Newton's laws of motion and say that probably, I'm not sure, but probably the answer should be P2 minus P1 is equal to rho times G plus AH. Because if we are going upwards, the pseudo force will be downwards. The effective gravity will now become G plus A instead of G. So it should be that. But we need to derive it rigorously. So I'm going to derive it properly and try to show you whether this result is true or not. How do we derive it? We derive it the same way we derive this particular result. We take a small cylinder. Let's say the area is delta S. And we could solve this in either the ground frame or this accelerating frame. I don't want to use the concept of pseudo force, so I'll solve it in the ground frame. So in the ground frame, this particular liquid has a force P2 delta S acting on it upwards. It has a force P1 delta S acting on it downwards. It has a force mg acting on it downwards. So the net force upwards for this object will be P2 delta S minus P1 delta S minus mg. If this liquid were at rest, this force would be 0, but this part of the liquid, just like the whole liquid, is accelerating upwards with an acceleration A. So the force should be equal to the mass of this liquid multiplied by the acceleration. So that will be equal to m multiplied by A. From that you can just see that we've already gotten this result. P2 minus P1 is equal to G plus A times m. M can be written as rho into h into delta S, and delta S cancel. So we get this result. So in a stationary liquid, P2 minus P1 is rho GH. When the liquid is accelerating, we can just use the concepts of pseudo force, or we can actually derive it directly from scratch, and this is the result we get. Right. Similarly, other problems you can do in which liquids are moving in an elevator or accelerating, because the important thing is not to know this formula. If you just knew this formula, then it would be harder for you to solve this question. But if you actually knew how we derive this formula, which was basically using Newton's second law, then you would have absolutely no problem solving this type of question at all. Another form of question in which liquids can be accelerating, and you've probably seen this before as well. We have a liquid, it is at rest, so the surface will be horizontal. If we start moving this with an acceleration a towards the right, we notice that the surface tends to become slanted, it doesn't stay horizontal as well, right? So we need to calculate this, we need to find out why that is happening. And what is this theta? We could have been asked to find a number of quantities. Let's say we are asked. So again we'll do the same thing, but now we'll take two horizontal points and we'll make a cylinder. If there was no acceleration, P1 had to be equal to P2, right? We derived that earlier, saying that when the liquid is in equilibrium, the horizontal levels will all have the same pressure. That does not necessarily need to be true now. So now what needs to be true is, let's say this area is delta L and this is delta S and this length is L. So on this liquid there's a force acting towards the right, P1 delta S. There's a force acting towards the left, P2. There is also mg acting downwards, but mg will be balanced by the force due to the bottom of the liquid upwards, and we are only concerned with the horizontal direction, so I'll not write that, right? So the equation will be P1 delta S minus P2 delta S is equal to this liquid's mass times A. So that will be rho of the liquid multiplied by delta S multiplied by L, that is the mass of this liquid, multiplied by A. So from that we get P1 minus P2 is equal to rho AL. Okay, now what we needed to do was we need to find out this tan theta. So what we can do is we can take these two heights as H1 and H2. Okay, so what is P1? P1 is the pressure at this point plus H1 rho g. That is still valid because there is no acceleration in the vertical direction, right? So in the vertical direction, P2 will be P1 plus H rho g. So P1 will be this pressure plus H1 rho g. So that is P atmospheric plus H1 rho g minus P atmospheric plus H2 rho g is equal to rho AL. This gives me, P atmosphere will cancel, it gives me H1 minus H2 rho g is equal to rho AL. Rho cancel, which gives me H1 minus H2 by L is equal to A by G. But what is H1 minus H2? That is this particular height. And what is L? That is this particular height. So this by this is tan theta. So we found out the relation that if we accelerate a liquid with an acceleration A, this angle tan theta will be equal to A by G. So if the acceleration is equal to gravity, it will tilt at an angle of 45 degrees. To make it completely vertical, we would need to approach an infinite acceleration because theta is pi by 2 when this particular This gives you an explanation of why the surface of the liquid is not necessarily horizontal when we accelerate the liquid in the horizontal direction. Let's move on to a couple of other smaller concepts which are left. One is the concept of streamlined flow. So when liquid is passing through a container, let's say through a pipe, there are two types of motions it could follow. The more easier one to study is called streamlined flow, and then the opposite of it is turbulent flow. So streamlined flow basically just means regular flow. It means the motion of the fluid is not necessarily changing rapidly with time. The technical definition of it is, if we have, let's say, a pipe like this, then every particle passing through this particular point, remember the fluid is going in this direction, coming out this direction, every point of water, every molecule of water that is passing through this particular point has to have the same velocity, that is the same magnitude and direction. So if there's a particular point passing through here and goes through here, 10 minutes later another point which passes through this point will have to move through this point, and that is true for every point in the pipe. So what that means is all these lines will have regular line, we call these lines of flow. This is in which direction the molecules of the liquid will move. This particular molecule will always move in this direction. It will never move in any other streamline. This particular one will always move in this streamline, right? So these particular lines are called streamline, and when the motion is this regular, it is called streamline flow. As opposed to that, there is turbulent flow, which you've probably seen in rivers or when waterfall reaches the riverbed, and the motion is quite erratic and quite irregular, and it would be very hard to actually calculate the mass or the acceleration of any individual particle of water. Right? So this is streamline flow. These lines are called streamlines, and streamlines have a particular property that they never intersect. And the reason they never intersect is because a particle once starting through this point will always move along the streamline. If it intersects another streamline, then that means the particle doesn't know along which streamline to move, and that is a contradiction. So these lines are called streamlines, and this particular motion line flow. The opposite is called turbulent flow. Right. The final important thing which is left is equation of continuity. Sorry, that's not the final thing. We still have Bernoulli's equation after that, which is very important. So the equation of continuity basically says that if this is a pipe, cross-sectional area changing with time, let's say here the area is A2 and here the area is A1, and let's say streamline flow water is entering with a velocity V1 and exiting with a velocity V2. Okay, so this is not the end of the pipe. The pipe goes along for infinity. I'm just making two sections. The very first assumption we made about the liquids was that they are incompressible. That means the volume of the liquid within this particular pipe will stay the same. It will not increase or decrease. The liquid cannot compress. So that means the amount of water entering this pipe per unit time will have to be the same as the amount of water exiting this pipe per unit time. Right? In delta t time, what is the amount of water that will enter? So in delta t time, if with this particular length is V1 delta t, then this particular volume of water will enter this pipe in delta t time. Similarly, in delta t time, V2 delta t would be the length. This particular amount of water would come out in delta t time. We know that both of them have to be equal. So A1 V1 delta t is equal to A2 V2 delta t. Delta t delta t cancel. We get the equation of continuity A1 V1 is equal to A2 V2. A very important result. It just says that as the cross-sectional area of the pipe decreases, the velocity increases. And we've seen that in taps, obviously. When you have a tap, the water generally, you've probably seen it, flows something like this. The cross-sectional area is high and it keeps on decreasing. That's because as the water is falling down under gravity, its velocity keeps on increasing. If velocity is increasing, then the area has to decrease, right? So this is the equation of continuity, which tells us how to relate two particular areas of cross section and their velocity. We start Bernoulli's equation next time. Thank you.